Okay, so last time we already have investigated in the change of the energy, and we have seen it is not simply the electromagnetic energy as written here, which we know we can simply compute. Here is the energy density by the magnetic part and the electric part. We get an additional part with us, and that is, as we see, it's a surface integral of the cross product between the electromagnetic field and the electric field. And we call this the Poynting theorem. It's the work energy theorem of electrodynamics. In a low frequency regime, well, we will not have to consider this additional integral. Yeah? But especially, at least when you go towards electromagnetic waves, this is the important part, because with this you get the radiated power of an antenna, for example. Yeah? And that we will also discuss in detail clearly in our last chapter about electromagnetic waves. And for this, we have introduced, for this physical quantity, the cross product between E and H, or E and B, and scaled with 1 over permeability. We have introduced here that this is the so-called Poynting vector, and we have seen that this is a kind of an energy flux density, as it is called, because we look at changes of energy. However, you are fully right that perhaps we should write according to the unit a power, yeah, because according to the unit S is intensity, so we have here power per square meter, yeah. And perhaps I should also write here yeah, here perhaps we write it here, that this is the intensity. Okay. So in this sense, if we have this look to Poynting theorem, just summarizing the total change of the energy, we have what changes towards the stored energy, electromagnetic, the electric and magnetic energy, and what goes out or in over the surface via this intensity, the Poynting vector. Now, clearly we can, when we set the change of the energy to 0, we should come to the conservation of energy. And then we see that the change of the electromagnetic energy given by the energy of the magnetic field, the energy of the electric field, is here for the following. It's what goes over the surface. So this volume we are considering the enclosed surface, this partial omega, by our intensity, so the Poynting vector. And here we clearly apply then the Gauss theorem, so that we come back from the closed surface integral to the volume integral. We consider therefore the same volume integral, we neglect the volume integral, and we get it in a differential form, that the change of the electromagnetic energy in a conserved state is equal to minus the divergence of the Poynting vector. Yeah? So you see in this sense that our charges on the one hand generate the field, on the other hand electromagnetic fields do work on charges. So you have the full interaction between these quantities. And we also know that everything from the physical point of view, as we discussed in electrodynamics, goes back to charges, also the magnetic field, not only the electric field, where we discussed about the eigenspin, for example, of the electrons. Okay, you can also have mechanical energy in your system. Then it's simple, you just add to the electromagnetic energy the mechanical energy. Yeah, and then we have in our sense just this extension that we have the change of the energy density, which is the superposition of the electromagnetic energy density given by the electric field plus given by the magnetic field, and you just add also what you perhaps have due to mechanical forces acting in your system, and that is balanced by the divergence of the Poynting vector. And it is also very interesting to compare this to our continuity equation, yeah, where we know that the divergence of the current density, again here minus, because we have put it on the right hand side, is balanced by the time change of the electric charge density. So this charge density now in our theorem are the energy densities, and the current density itself is our Poynting vector. So we also have here a relation to our continuity equation and can interpret it as follows. We will also later on have an example and look there for a low high frequency part, and especially this will help us a lot when we will consider wave propagation, electromagnetic wave propagation in our last chapter. Let's have a very simple example. Yeah, this should be fulfilled clearly for any case. So we have a very simple setup of a wire with a radius A and length L, as you can see here in this sketch, the radius, the length. Yeah, and we know if there a constant current is flowing, or you apply a potential difference given here by the voltage U, then the electric field here has just a axial direction, and it is just this voltage over the length. On the other hand, and this is within our wire, but also on the surface. Yeah? If we consider the magnetic field, we know we have to differ between what we have inside and outside. We have discussed this for a constant current. Now, since we will consider the power and we have to integrate over the surface, we immediately write down the magnetic field at the surface. That is why we have here the simple relation where the distance r is exactly the radius a of our cylinder. Yeah? And we know it is clearly going in circumferential direction, so around the cylinder in closed field lines. If we compute now the Poynting vector, as we have discussed, so we take here 1 over the permeability we have here and the cross product between the electric field and the magnetic field. Then we have the cross product looking at the direction of Ez cross E phi, and we get out ER. And in this sense, then we have here just the multiplication of the amplitudes we have in front of the directions. And if you integrate now over the surface, we should get out the power. And as you see, since this is all constant, the surface is also within the denominator, and this cancels out. So we just have the surface, 2 pi radius length, radius is A, and what we get clearly out is here then voltage times the current. So this is consistent in this sense that you can also apply it to this simple static case, as we have considered here a part of a wire and the current, a constant electric current is flowing through this wire. Okay, now, you know, a very important thing is that we like to go to the frequency domain, which simply speaking, engineering is often done by just using complex numbers, but at the end it is a Fourier transformation exactly for this one frequency f or angular frequency omega. We always have our time domain representation. We have now harmonic fields, so we have any excitation at the constant frequency f, which is also within our angular frequency omega 2 pi, which is 2 pi f. And we describe it by two important parameters. We clearly have the single frequency in the cosine or sine function, and we need here now a vector, because we describe a vector field with the x, y, and z component, which are the amplitudes in x, y, and z direction. Therefore, I have here this hat on this value, and it is a vector because we have these three parts. And what we also have here, and you mainly write it in this sense, that there is also a phase phi, in this case E for the electric field. And since we will also consider then for other physical field vectors, the index will always describe us which phase it is of which field. Okay, so you see explicitly I have written down it in this sense, the three components of this amplitude vector. So it's the absolute value of the amplitude of the complex value Ex, yeah, it's in this sense of the complex value in y direction and the complex value in z direction, or you write it already in this sense with this, as written here with the hat here, so that you see what is exactly behind. And then we can write it down as shown here as a complex number, and that is shown by the underline. Yeah, so E as a complex number, we know it changes according to our frequency, better speaking, angular frequency omega, which we have now with our exponential function, and we have to take the real part. We know according to Euler that this exponential function is the cosine plus j the complex unit, square root out of -1 sine, and if you take the real part, you just get out the cosine function, and so it is in this sense possible. We can now treat this separately as shown here with amplitude and phase. The phase clearly is also in the exponent, and we know when we take the real part, that's why we get back as shown here to the cosine of this argument, where we not only have omega t but also the phase. Yeah, on the other hand, we also know that we can write this down by the conjugate complex, which is shown here by this star, that it's 1/2 the quantity, let's say, in our case it's a vector, but could be also clearly a scalar, and the conjugate complex as shown here. And then we have clearly in the argument of the exponential function, because we take the conjugate complex of the whole part minus j omega t. Okay, this is also then in this sense written here. If you just look at this E underline and you take the complex conjugate, we know we just take this minus j phi, which is the phase, because the hat component is the absolute value. Okay, now we had exactly this term here considered. So let's compute out what is the dot product between the current density and the electric field. Now we write it down here according to the expression we have written here. So we use this expression here, both clearly for the current density and for the electric field. That is why we clearly also have here 1/4, yeah, because you know we have this decomposition in this sense, and then we have to take here 1/2 of the value plus the conjugate complex value. Now, if we do the multiplication and we look, so we have here terms where we have the exponent j omega t, exponent j omega t, gives us 2 times j omega t, or 2 times, as shown here, minus j omega t. In this case, it is dot product between j and e, and here the conjugate complex of j dot product with the conjugate complex of e. And then we also have these mixing terms, ones with the conjugate complex of j and the electric field. The exponential function clearly here adds up to 1. And we have the part where we have here this j and e conjugate complex, and you get this value here. Okay, so in this sense, we can combine it and can write it as follows, that it is 1/2 of the real part of j complex conjugate dot product with e. So these are these parts as shown here. And this gives us, if you look it up and you would explicitly write it down, you can combine it and get 2 times. And here with this exponent, because if the exponent is plus or minus, when you take the real part, it's the same at the end. Yeah? That is also the case why we can combine here these 2 terms, because we take the real part, yeah, it's the same, these 2 terms by this part here. Okay, so that means if we take the real part, yeah, then once, since the conjugate complex make the exponent of the exponential function e to minus, we have here then the difference between the phases. Omega t cancels out because we have once plus omega t, once minus omega t, and here it clearly adds up. We have 2 times omega t. Okay, so you can rewrite this term here when we express it in with this exponential or Euler formula according to this part here, yeah, which gives us the real part by this term here. And if you integrate now over the time period, then clearly what cancels out, if we look here, is this part here, because if you have a cosine or a sine function integrate over 1 period, and if you have the frequency directly or twice the frequency is not of interest, you have exactly the same amount of area positive as negative. Yeah, so this cancels out, as you know, and so we simply know, I just wanted to again write it down, that you take just 1/2 the real part of j conjugate complex dot product with e. So it's the same as you have already done this, let's say, for scalar quantities, for current and voltage in this sense, and computing here the power. Yeah, the proof, as we know, is simple. We can, without doing it and going to the complex numbers, let's say, or frequency domain, we clearly can do it fully in the time domain. And in the time domain, then we know, since we have a cosine for the current density and the cosine for the electric field E, and they have here just the different phases. You know that we have this identity of cosine alpha, cosine beta, that we can write it once with the difference of the arguments and once with the sum of the arguments. And then we clearly get, as you know, also here the difference of the phases, and here we get a cosine with 2 times the frequency, which again, integrating over 1 period cancels out. And we all know that what ends up here are the peak values of the current density, the peak values of the electric field intensity over 2. Yeah? So it would be the same as you take here. You could also take the root mean square values, so the effective field, yeah, as we know, when we have current and voltage, so any network parameter. So it's the same if you also do this for the field quantities, and there are no difference in this sense. Okay, now we will do some rearrangement with our Maxwell's equation, and here I have written down the time harmonic case, so just the frequency transformation of the first Maxwell's equation, as we know here, where the curl of the magnetic field is equal to the current density in conductive bodies plus the displacement current density, which is the time derivative of B. When you do a time derivative in a frequency domain, it is a multiplication with j omega, which means, since I put it to the left-hand side, we have here the curl of H. The underline always means we are now in the complex domain as well, which is equal to the frequency domain, minus, clearly because we have put it from the right-hand side to the left-hand side, j omega d is equal to the current density. And on the other hand, we have the differential form of Faraday's law, where the curl of E is equal to minus the time derivative of B, the magnetic field. And then clearly we have here the curl of E, again, is a complex value is equal to minus j omega, because the time derivative gives us the scaling with j omega. Okay, so now we have our term, as we have seen before. We have this term where we integrate over the volume the conjugate complex of J dot product with E, and we now substitute here in this sense J, so the current density conjugate complex. Yeah? That is why we have here the curl of H conjugate complex, and be careful, we have here minus j omega, so a complex number which just pure imaginary, and here the complex number d. If you take the complex conjugate, you get plus out of minus j omega plus j omega, as you know. It's a pure imaginary part, and we should not forget that also d has to be taken conjugate complex in this sense. Furthermore, we want to express this term we have here, that we want to get in again something like the divergence of a part, because then from the volume integral by a Gauss theorem, we can go up to the surface integral, the closed surface integral. And we have the vector identity that the divergence of E cross product with H conjugate complex can be written down as H dot product with the curl of E. We know the curl of E we can substitute here by minus j omega b. And the second term of this identity is then E dot product with the curl of H conjugate complex. Okay, so we again have the term which we want to express by the electric and the magnetic fields. So we now have here the following, that we express this term here, yeah, which we also have here, this term. We should not forget that we have a minus. That is why we have here the minus of the divergence of the cross product of E and H. And we have here this additional term, which is coming from here with minus j omega b dot product with H conjugate complex. Therefore, we have this minus here. Yeah, and we should not forget this term at the end here, where we have the dot product between E and D conjugate complex scaled with j omega. This j omega is in front of the parentheses. Okay, so we nicely see that what we have obtained now by introducing or substituting Maxwell's equation is that we have obtained here this term which we clearly can, so this term was too much without the, I wanted to have it without the divergence operator, which we know is nothing else as our pointing vector, and the terms we have here are clearly energy densities, electric field, and magnetic field. Yeah? To be precise, as written here, we have here then 1/4 as a scaling factor, which we have to put in when we substitute these expressions, yeah, which we will substitute in here. That means that putting now all to the left-hand side, we see that the Poynting theorem we had already discussed in the time domain, in the frequency domain, is now our first term here, where we have the current density and the electric field, which is an ohmic term, as we know. Yeah, that is the ohmic term. Then we have here our energies according to the magnetic field, inductive term, and due to the electric field, capacitive term. And we have again, clearly, as we had the time domain, this additional term here, and that gives us the flux we have, or better say intensity, given by the cross product between E and H, which is going out or in of the closed surface. If we have lossless dielectrics and perfect conductors in this sense, and meaning that we can neglect any losses in coils, for example, or in capacitors, then clearly our energies there will be cancelled out. Please also note here that we will also need, we have here J, so the complex unit 2 times omega. And if you have no losses here, then we have the pure inductive part and the pure capacitive part without losses. And if you take the real part of this, this will be then 0. If you have losses, yeah, and you take a real part, that means that the magnetic energy and the electric energy is pure real, yeah, if you have no losses. They are pure real. Since you have the multiplication with j omega and you take the real part, the whole term here is pure imaginary. Taking the real part is 0. And therefore, without losses, in case of lossless dielectrics, perfect conductors, we have here, in this sense, then this relation here. On the other hand, again, with losses, we have to consider this term here, yeah, because then we will have a complex value for the magnetic energy density and electric energy density, and the imaginary part of them describes the losses. And here you multiply with a pure imaginary part, so the imaginary part of the magnetic energy and the electric energy gets real value due to this multiplication. Okay. So it is then clear that when we have dissipation, our energy densities will have an imaginary part, and therefore we have to take this term here of the magnetic and electric energy into account. Otherwise, since at the end we always take the real part, they will cancel out, which is coming due to this scaling with a pure imaginary value, which is j 2 times omega. Yeah. Exactly. Yes, yes, exactly. And the magnetization we have. Yeah, yeah. We will also come here, that is very interesting, that with the pointing vector, you will also be able to describe the magnetic losses, for example. Yeah, and we can then really separate the resistive losses from, or eddy current losses in a ferromagnetic material we are investigating from the hysteresis losses. Yeah? That we will see. There is always a problem in measurement technology. You want to get the hysteresis losses, but the setup you are using are sensing coils, and so you need a magnetic field which is changing over time. But you know, when you have a magnetic field changing over time, and you have a conductive body, also our ferromagnetic materials, like the steel sheets in transformers, have some conductivity. So you induce some eddy currents. The question is how you can separate the eddy current losses from these hysteresis losses, the pure hysteresis losses. Okay, before we come to this, let's have another example here. We have a two-terminal linear passive electromagnetic system as shown here, and we apply here a current to this system, and we will see that we also have to take into account if the frequencies are increasing and increasing, also the radiating energy out of this system. However, in any case, how the system looks like here, just characterized by the impedance. Yeah, we assume you just have passive elements, resistors, inductors, capacitors there. But as we know, we will also have, if we have accelerated charges, that means you have an AC current to it, and you increase and decrease the frequency, you will also have radiation. And as we already know, this radiation part will be described clearly by the pointing vector, and we have to integrate over the surface. Now, from the complex power on the input, clearly we have to take here the current and the voltages. The underline again is that we write it down in the frequency domain, and therefore voltage as well as current are complex parts, but we know they have the amplitude and the phase. Yeah, and if you take the real value out of them, in addition with the frequency with which they have, you get the time domain function. So at the input, clearly we have this relation, and please consider this is here just a surface integral which considers here this part of the input we have. Now, let's apply the pointing theorem to this example here. So, we know that this input power we have is balanced, as we know, by any losses we have in our circuit. And you know, you have ohmic losses, yeah, which are here, this part. You can have inductive and capacitive losses if you consider that your dielectric material due to polarization, or your magnetic material due to magnetization, have losses. And we also have to consider what is radiated by the intensity which we describe by the pointing vector. Here again, we clearly have to take from the surface away what is coming here in due to the current voltage part exciting the circuit. Yeah, and what we clearly know is then, as you also do in network theory, this impedance we can decompose in R plus Jx, and in a complex notation we have that the voltage is the impedance multiplied by the current. Always the underline remains us that we now write it down in the frequency domain. Yeah, and if you look here at the resistance, we just take the real part of the impedance, And since on the left-hand side, we have here 1/2 conjugate complex of the input current and the voltage at the input terminals, we have here to take the real part of this term here. Then we have the radiation term. You do not see here a real part, but we assume that what is radiated at the end is real. Yeah. So that S is really just real and has no imaginary part. At this stage, we cannot prove it, but when we will go towards the waves, we will see that at some distance we will decompose again in the near field and far field. At some distance where we are at the far field, it is also called the radiation resistance you have of your antenna is pure real. In the near field, you will always have also reactive parts, and energy is going forward, backward. Yeah? And what is really radiated at the end, yeah, these waves which are radiated and you can receive in the far field will be pure real. Yeah, and since we have here this j omega, we have here to take the imaginary part. Yeah? Why we have here this 2 and here this 4, we have here 1/2. Yeah? And therefore you get here these additional terms 2 as well as 4. Okay, so you see this is the expression you would have to evaluate in order to get the real part, and in order to get x, the imaginary part. Again, you see we assume that this is, perhaps I should write it down, that this is pure real, and what is, yeah, clearly you have to divide it by the absolute value of the current squared, otherwise it's not a resistance. But we call then this part we have here. So perhaps I write it. So this part divided by the absolute value of the input current squared is the radiation resistance. And as I already write resistance, you see it is a pure real part. Yeah, and in this sense, now we see for the imaginary part, we have to take here the real part. That's again because we got in here J, our complex unit, and clearly the imaginary part we have here of our ohmic term. And if you go to low frequencies, yeah, for low frequencies, what we really have are the real part where we simply can write this here in this sense that we neglect that there is perhaps also some additional induced eddy currents due to Faraday's relation. We just have the ohmic part, and for X, then we just have the balance between the magnetic energy and the electric energy. So you see that we neglect any imaginary part we could have here, yeah, and we neglect here clearly this part as well as the radiation. That is something which is really just coming up if you have higher frequencies. So this would be the approximation, and with this we get the ohmic losses. These ohmic losses are the main parts as we know. However, if the frequency is increasing, as you know, then clearly you also will have to take part which is induced due to time-varying magnetic fields, which is described by Faraday's law, and inducing any eddy currents, for example, in your structures. That would be again what we have discussed, yeah, with the simple setup of a coil and the plate, yeah, where we have seen that the imaginary part of this magnetic field is really concentrated at the plate, and that is due to the eddy currents, yeah, which are generated according to our relation coming from Faraday's law, that a time changing magnetic field generates the curl of an electric field. Are there any questions? Pointing vector, I guess you have heard already in, not really. Yeah, it depends. So you are in the, which semester? Okay. Okay, so this is a demonstration that it is not only interested in any networks we are analyzing and perhaps even at high frequencies, where this additional part which comes in due to Poynting's vector going through the surface of the volume we are considering, but it is also interesting for a standard investigation we do for ferromagnetic materials. So in this case, what you see here is nothing else. You have, or perhaps I show it here, you have a ring made of a ferromagnetic material. And we are interested there, what is the losses there, which are made of the hysteresis losses. So we just consider here the magnetic energy density, and clearly, since we will excite here with the AC current, we will also have some eddy current losses, because the material, the ferromagnetic material, also has some conductivity. So what is shown here is then you put a coil around this ferromagnetic core, and you have then an excitation coil, and with the excitation coil you generate a magnetic field as shown here. Let's say this is going in this direction, just Ampere's law. As we know, the right-hand rule, we look in which direction the current is flowing, and we know in which direction then the magnetic field is going. Here, please consider the coil, the wire is wound around the core in this direction. Huh? So in this case, the current is going in circumferential direction, generating you a magnetic field being concentrated in the ferromagnetic material, because the ferromagnetic material has a high permeability and therefore will guide the magnetic field, and you will have very few stray fields. That is also why you use this geometry. So this setup with the diameters you should use, the cross section you should use, the number of turns for the excitation coil and the number of turns for the measurement coils is normed. Yeah? So that you can also look up in this section. Okay, so we are interested here in the average power, yeah, which we know it's just the time change of the energy in our system we have, and then we get the power density, and we integrate, we get the total energy, so the time change is the power, and when we average this over one period, the period is given by the excitation current, we should get the average power. In this sense, the losses we have there, which will be on the one hand due to the ferromagnetic material, so the magnetization process we have there, and on the other hand, since we induce eddy currents, we also will classically have our ohmic losses. Yeah, and according to our theorem, we can describe this by the divergence of the Poynting vector. Yeah? So we have to integrate this over the volume and then average it over the period t. We know that the Poynting vector is expressed by the relation, the cross product between the electric field and the magnetic field here already expressed by H. So we don't have the scaling with 1 over permeability when we would use here B in this sense. And we also have this minus, yeah, as we had it in our theorem before. Now, it is clear we have here then a magnetic field in this sense, which will also be able to describe the magnetization process. And we also have here this electric field where we have general Ohm's law to get a relation to a current density, which is also shown here. Yeah, you know, when according to, perhaps I should write down, according to this relation, if you have a time magnetic field, and perhaps I should also put in that we have here, and I write it already, the solenoidal part, as we have discussed quite often. Here, any irrotational part will be cancelled out by the curl. So we can write here that this solenoidal part also of the current density, which perhaps is very often written with the index E for eddy current. Yeah, here we clearly have the classical, again, classical Ohm's law, that due to the conductivity of the material, so the gamma, we get a relation between this eddy current density, which will go, yeah, here within the material and will be generated due to the solenoidal part of the electric field, which itself is occurring due to the time changing magnetic field. Yeah? And that is due to the fact that we have here coils around the ferromagnetic core, and we put a AC current to this excitation coil. So this red coil is an excitation coil, and this white wire will be a measuring coil. So this is the standard setup. Okay, so we should be aware, that's important, always to see in which direction which physical field is going. Now in this sense, since again the excitation coil is put around the core, the magnetic field is going here in the ferromagnetic material, and then according to our Faraday's relation, we will have here this closed field lines according to the induced eddy currents in the core, which are exactly orthogonal to the direction of the magnetic field. Okay, so when we substitute this, so as you can see, I have already written down the first Ampere's law. We clearly neglect our displacement current. We are at low frequencies, so this is not of interest. And I already wrote here the current density of the eddy currents. Yeah, so this is not any excitation current we have, because what we consider is the situation we have here within the ferromagnetic core, yeah, made of this ring. Okay, on the other hand, this eddy current density is actually generated due to the time change of the magnetic field, generated by the primary currents with which we load our excitation. Yeah? And for this, we get then the vorticity, which is the curl of the electric field. And this is already reduced to the solenoidal part of the electric field, because any irrotational part, source sink part, will be cancelled out by the curl operator. Yeah, and we also have our constitutive equation. Now, what we will do is we will try to express now our Poynting vector as we have here in our formula by this relation. So the divergence we have here of the Poynting vector, we can rewrite here by this identity that it is just the curl on the electric field, dot product with the magnetic field, minus the curl of the magnetic field dot product with the electric field. And the curl here of this solenoidal electric field became, according to this relation here, substitute by the time derivative of the magnetic field, and the curl of H, as we have it here, can be substituted by this induced eddy currents, which are flowing here, which are flowing here in this direction in closed lines. Okay, so now let's come back to our formula for the losses we have there. So we have to integrate here over one period. And in addition, now clearly we have to integrate over the volume. Now let's look here what we have. This term is H dot product with the time derivative. We also have this minus. We should not forget we had here this minus. Yeah, so this minus cancels out with this minus. That is why we have here a plus. And then we have the additional term where we could substitute the curl of H by the eddy current density J index E. Okay, so in this sense, this is our second part here, and we also have to integrate over the volume and over the time. Now, when you investigate here, this term here, we have here the time derivative, so we can, this time derivative cancels out, and we can write here the dot product between H and dB, and then have to integrate clearly over the limits from one P1 to some P2. And on this part, we already have substituted according to our general Ohm's law. This is not nice because we can make it shorter. According to this, we can use this and substitute here the electric field, the solenoidal part of the electric field, which gives us then this second term. So here is the first term, which we already also have, in this case, discussed concerning any nonlinear or hysteretic behavior of a ferromagnetic material. And here it's the typical ohmic losses we have here due to the eddy currents flowing within our ferromagnetic ring structure. Yeah? And this part here are the total hysteresis losses, and this part here gives you the eddy current losses. Yeah? So you see that even with this idea we had, with this theorem, pointing theorem, we could here write explicitly down for this setup where we investigate the losses in such a ferromagnetic core, where we also have a conductivity and clearly we have hysteresis behavior. We can describe here by the pointing vector, where we have used instead of the surface integral, the volume integral, and therefore we had to take the divergence of the pointing vector. And that is actually done also in practice. So we have a strong research on this part in order to get with such measurements and such relations the material properties out, so we can put them in our constitutive equation, especially in the hysteresis operator, so that we can then also do very precise numerical simulation of ferromagnetic force. Or when we are looking for transformers, it's the same. There, you know, we have these steel sheets, ferromagnetic steel sheets, which are very thin, in order to make the eddy currents small. Yeah, so that this ohmic losses, so this second part, The second part is clearly small. This part, well, we cannot really influence in this sense with the geometry. Here we need special materials which make these ohmic losses small. Yeah, but that is also a key part of producers of these electric steel sheets to make the material in such a sense that the hysteresis losses are as small. Yeah, because you know we have AC current, so we always magnetize it plus minus. Yeah, and you always go along your hysteresis curve. Yeah? And the cross section you have there, the area in this hysteresis loops are direct proportional to the losses you have. Okay, other questions concerning these rearrangements? So we again have used here this pointing theorem and could even get a nice decomposition between the eddy current losses you have within a ferromagnetic material and the hysteresis losses. Yeah. This part here. Of course, of course, of course. But perhaps, okay, I should. So actually, perhaps I have not written. I have made no sketch. So you have here H and B, the amplitudes of H and B, and we assume we have an isotropic material. Yeah. Now, when you have a constant frequency in your excitation current, then you will go, for example, like this. I hope I get it somehow. Yeah? Then this will be how you go around. Yeah? And as I have told you, this area is proportional to the hysteresis loss. So you want to make this as small as possible. Yeah, and you know we have here perhaps we call this value PR. So PR is the remanent magnetic flux density, and this part is HC, the corrosive magnetic intensity. Yeah, and in this case, it would be good that these values are very small. Yeah, and then this area strongly decreases, and you have a material which will have small hysteresis losses. But you also see it's a question of the amplitude of your excitation. Yeah, this perhaps is excitation 1. Yeah, and if you have a larger current, yeah, then you will be able to drive the ferromagnetic material to even to saturation. Yeah, so perhaps for the perhaps I take here another, take this red one. If you have a smaller excitation, then it will look like this. So this is 2. Yeah, and we can simply write down that the current E1 is clearly larger as the current E2. Yeah? So it is not only a question of the material properties itself, how large this area is, it is also clearly a question of your excitation. Okay. Further question towards this idea to use the pointing vector in order to get this decomposition in the eddy current part and into the hysteresis part. Okay. Okay. I would say that was a different. Yeah, here I am. Okay. That was this part. Okay. So the last part of this investigation towards the conservation equation, as you know, was to look at a very ugly term we will see at the end, but which is the main term you implement in any numerical simulation program in order to compute electromagnetic forces. And yeah, there was. Oh, okay. So in this sense, we know our electromagnetic forces here described by the Lorentz forces, where we have here the term of the charge density rho and the electric field E, and we have the current density cross product with B. And now, when we use Maxwell's equation, and that will be now our starting point, we start with our standard expression for the Lorentz force, and then we will put in our Maxwell's equation and want to get at the end an expression according to the electric field E and the magnetic field B. Okay, so now in a first step, we use here the charge density and put our Gauss law in here. Yeah, we know that Gauss law tells us that the divergence of E is equal to the charge density over epsilon 0. Yeah? So you have here epsilon 0 divergence of E and scaled with the vector E itself. On the other hand, we have here a relation which is the first Maxwell's equation. I write it here down, where we have the curl of H, always write with B. Yeah? So we have here, I write it in this sense. Then we know we have here the current density, and here we have the displacement current density. We assume that we are in vacuum or we are in air, something. Yeah? This sense. And this can be also written clearly by epsilon 0 dE dt. Yeah? So that is why we get here this first term. And why we get here this second term. Yeah? So exactly when you collect what I have written down here, yeah, then we get and express the current density J by the curl of the magnetic field and the time derivative of the electric field. Furthermore, what we explore here is the product rule. So what is in this sense clear, if you have this time derivative of the electric field cross product with the magnetic field, we can take first the cross product and then the time derivative, but then we have too much because on this side we just had the time derivative of the electric field. Yeah? So we have to subtract here, according to the product rule, the electric field cross product with the time derivative of the magnetic field. Yeah? So this second part has to be subtracted. Otherwise, that would be not correct. And we know now from Maxwell's second equation, which is coming from Faraday's law, that we can express the time derivative by minus the curl of the electric field. Okay, so in this sense, now we already have used here this reformulation of the Lorentz force, and by the help of this vector identity, we now get here the Lorentz law, in this sense that we have the first term as we had, yeah, and then here this term where we have the time derivative of the electric field cross product with the magnetic field. We can express purely, as you can see here, purely in this sense by the curl of the electric field. That is why we have here the electric field cross product with the curl of the electric field. Yeah, that is due to this part here, this minus we get here in. And in addition, we should not forget we also have this part here, and that, where we have the curl of B cross product with B. I have just interchanged here the cross product between the curl of B and B, which means I have to take a minus. Yeah, therefore I have a minus here. Yeah, you know, you have to be careful if you take a cross product and you exchange the vectors, then you have to put a minus in front of it. Yeah, and the term we have in this sense obtained here, the time derivative of E cross product with B clearly gives us here then the cross product is the Poynting vector, and the time derivative clearly remains. Yeah? That was the trick, that I rewrote this term here by the time derivative of the cross product. So I get here in the Poynting vector, and I have to subtract clearly this term, otherwise here I cannot write that this equation holds. Okay, so I would say now our equation is even more ugly. What is perhaps not so nice is that it's a little bit different compared to the electric field and the magnetic field. So here we have B cross product with the curl of B. Here we have E cross product with the curl of E. That's okay. But here we have a term which doesn't pop up. But that's not a problem. We can take this term, yeah, for B and add it here, because the divergence of B is 0. Yeah. So now we extend even our ugly formula, because we know that the divergence of B is equal to 0. So we can add this term there, divergence of B, and scaled by the vector B itself, because again, I write it here because this is equal to 0. Now, we also try to reformulate a further part, and that is this part here. So by vector identity, you can write a physical vector field, E cross product with the curl of E, by 1/2 the gradient of E squared. You know, E squared means E dot product with E. So this is the scalar, and you can take the gradient, minus the dot product between E and the nabla operator, and this is operating then on E. So this term here, which pops up here and which pops up here, we can substitute by this vector identity. Okay, so you see that this y according to this equation here, this additional term comes in and this term comes in, yeah? As well as on this side, this term comes in and this term comes in, and therefore you do not see that this cross product between E and the curl of E, as well as cross product between P and curl of P, will not show up here. Yeah? So this is now a really ugly term. On the other hand, you can introduce the Maxwell stress tensor, which is shown here. Okay, so this is now a double index we have on a quantity which we call capital T. The index is I and J. And you see what we have to do is we have once here the electric field and here the magnetic field. And you see that this is totally symmetric what you have to do. You have to take the product between the I component of the electric field and the J component of the electric field and have to subtract 1/2 of the electric field squared with the delta function Ig. And here is totally the same. Yeah. So now let's go here. What does this mean when we write Ei, Ej? Yeah. Then this gives you a 2x2 matrix in 2D, but let's go already to 3D. It's then a 3x3 matrix you call a tensor of second order, because that is E1, E1, which would be E1 squared. Yeah, and I write here perhaps down the field vector E, which we write down as E1, E2, E3. In Cartesian coordinates, that would be the X component, the Y component, and the Z component. Yeah. And you see, in this sense, perhaps it's easier when you have this index notation that you really write the X component as E1, the Y component as E2, and the Z component as E3. Yeah? Then, in this sense, it's easier. It's E1, E2, E3, the three components of the electric field. The same will be for the magnetic field. And in this index notation, always the second index is rotating fast. Yeah. So they are always going from 1 to 3, 1, 2, 3, which means the second entry will be E1, E2, yeah, and the third E1, E3. Yeah. So E as well as J take on the values 1, 2, 3. And the second index you have there, which is J, is always rotating faster. So for the first line of your tensor, you fix E to the first value, which is 1, and J takes on the value for the first entry 1, for the second entry 2, and for the third entry 3. Which also means for the second line, we have E2, because I is equal to 2. J again goes from 1 to 3. Yeah? So you have here E1, the diagonal entry would be E2 squared, but I explicitly write E2, E2, and the third one is E2, E3. And then we have here E3, because I takes on the value, the last value, which is 3, and again, J is going from 1 over 2 to 3, so we have here E1, E3, 2, and E3. And you will see when you have such operations, then perhaps even a divergence on this tensor here, it's easier to do it in index notation. I don't remember how to do it in, I always also have to look up when I use the nabla operator. So you see this Einstein notation then really makes sense. So you see in this sense that we use here these indices I and J, and then get here our tensor, or simply speaking, the 3 by 3 matrix. Yeah, and here you see what you have to subtract. You have to subtract 1/2 delta ij e squared. We know the delta function is 1 if I is equal to j, and it is 0 if I is different from j. So I also write this here down. So if you have here the delta function, so delta ij takes on the value of 1 if I is j, and 0 if I is different from j. So you see, this will just change what we have written down here on the diagonal entries. Yeah, the off diagonal entries, I is different from j, and so this will always be 0. Excuse? Can you? Yes, yes, in this sense. But it is not the identity, because identity would have ones on the diagonals and 0 off diagonals. You will have a value. They are different from 1, according to the amplitude of the electric field. Yeah, okay. I think I have missed you. Yes, I have missed you now. Okay, we can also write it down, yeah, because this is this double index, yeah, that is just how the values takes on, and this clearly gives us exactly then the identity matrix or identity tensor. Tensor has some additional properties than a matrix. Matrix is just an algebraic construction. Okay, exactly. If we compare these two, then we see this just looking like this. And you can, as you see, you can write it in a very compact, otherwise it would be not as compact. Okay, so we introduced here this Maxwell's stress tensor, and here, for example, we have explicitly written it down for one of the diagonal entries, as shown here. Then you see the 1,1 component is computed as shown here. Yeah, because clearly, I should write this down, because when we have e squared, then this is ex squared plus ey squared plus ez squared. Yeah, as we know. Okay, and the off diagonal entries are computed like this, because the delta function there is 0, and so we have just the mixing between the individual x, y, and z components. Yeah, and if you take, and that makes it now difficult, but getting in a straightforward manner with the index notation, when you take here the divergence of t, you get out a vector, and what we write down here is just for the I component of this vector. But generally, you write it like this, and this with the index notation, we will now see should be not a problem for us when we understand the index notation. So let's go back. So we had the partial derivative of the ij with respect to xj. Yeah? And that is the divergence, I make it a little bit bold here, of our second order tensor, which is the 3 by 3 matrix in this sense. Yeah? And as we know, the divergence of a vector is a scalar. So you see, you always have a reduction of 1 towards the order of a tensor, because a vector is a tensor of first order, a scalar is a tensor of 0 order. Which means, if you take the divergence now on a tensor of second order, you should get out a tensor of first order, which is a vector. Yeah? So in this sense, we see it is t1, 1 dx1 plus d1, 2 dx2 plus d1, 3 dx3. Again, j in this sense is going from 1 to 3, and we fix I to be 1 for the first entry of our vector. And if we take now the second entry of the vector, we have t2, 1, again a partial derivative with respect to x1, because j takes on the value 1. Now j takes on the value 2, and here j takes on the value of 3. And let's make also the last entry of our vector. Now I takes on the value of 3. J again goes from 1 over 2 to 3. And then you see that this will be the resulting vector you get out when you take the divergence on a tensor of second order. Okay. So I also will upload these slides here where I have written. Okay. So in this sense, just look what you get out here, and which is really quite ugly. And let's say how simple it can become if you are familiar with this index notation. So at the end, you can write down that this Lorentz force density is computed out by the divergence of the Maxwell stress tensor. And in addition, we have the time derivative of the Poynting vector. That again, in this sense, will be then a general new expression we have here for this computation. I just go back here, and you see that this Maxwell force tensor, why I write, okay, I don't know why I have written here force tensor, and I always tell you stress tensor, because what we actually here have is Newton per square meter. Therefore, it is correctly, this should be stress. But you will find very often in books that they call it the force tensor. Yeah? But we know force, stress is force per surface, so per cross section. Okay, and I think then also the evaluation by hand, or if you have to implement it in the computer, it is easier when you see this index notation, as you see this really ugly formula, which will be up to here. Yeah, this is the additional term which pops out also here. Yeah, but this ugly term with all the nabla operators and all the different variants here operating on E as well as B is really ugly, and gets quite nice when you use here this index notation. Now, if you have an electrostatic field, for example, which is very interesting in MEMS devices, where you make MEMS actuators, then you will have just this term. If you have any magnetostatic or even magnetodynamic actuator, but the time change is in a range that we can still model this with the eddy current case, and we don't need also the wave part, so full Maxwell, then this will be just the part you will evaluate. And it is done in commercial as well as clearly research finite element programs. Okay, other questions? This was new for you, this index notation? Okay. But I hope you somehow enjoy it. At least when you see this ugly formula and you see this nice, hopefully nice expression, and even if you then look here, how simple it is to compute the divergence if you know the index notation. Clearly, you can look up in any mathematical book, you will also find it, how you compute it with this nabla operator. So really the divergence that we are used to, and which is, I would say, easy on a vector, but which is a tensor of second order, but already a tensor of second order, it is really not easy to remind how to compute it really. So in this sense, I would say the index notation is easy. Okay, we will apply this, not today, because today we will finish now. We will apply this to a charged sphere, and we want to know the electrostatic force on the half sphere, and when we cut through on this section here. What are there the forces acting and how we can compute them? And there you will see that this is really complicated in an analytic form to apply the Maxwell stress tensor, and it's clearly easier with the Coulomb forces as we have learned. Anyway, you will see that you come up to the same procedure, and in any numerical program it makes more sense because it is a straightforward procedure for implementation to use the Maxwell stress tensor. Okay, thank you for your attention.